Hello, welcome to our Advanced RAG interview prep series. In this video, we will cover the first 25 questions and answers you need to master Retrieval Augmented Generation in 2026. This video is perfect for engineers, ML practitioners, software architects preparing for advanced interviews. In this video, we will cover fundamentals of RAG, reverse fine-tuning, hybrid retrieval, and scalable architectures, handling retrieval noise and multi-hop queries, preventing hallucination and optimizing context window, integrating structured data and agentic AI. I am Pradap Gopal. I am an AI architect with 19 plus years of experience. Let's dive in. Let's get started. Episode 1, Fundamentals and Architecture. Question 1 through question 5. Question 1. What is RAG and why is it important? RAG combines retrieval from external knowledge sources with generations from large language models. It is important because it reduces hallucination and makes AI answers grounded in real data. Think of it as giving your AI a library card. RAG solves major limitation in traditional large language models. 1. It stops hallucination. RAG forces AI to base its answers on retrieved facts like company wiki page or trusted databases, effectively reducing incorrect or made up information. It gives access to fresh data. Large language models have rich knowledge cutoff. RAG gives AI access to real-time, up-to-date information. It cites sources. RAG allows the AI to display exactly where it found the information, which dramatically increase user trust, accountability, and auditing. It gives integration with private data. It allows an LLM to answer questions using private enterprise data without the security risk of leaking that information into the model publicly trained. It is cost effective. Instead of costly fine-tuning or retraining an entire model to learn new information, organization can simply update the external RAG databases. Question number 2. How does RAG differ from fine-tuning? Fine-tuning bakes knowledge into the model weights. RAG keeps the model lightweight and retrieves knowledge dynamically. That means updates are faster and cheaper and no retraining required. Think about it. RAG feeds an AI real-time external data from a database at the moment of a query, acting like an open book test. Fine-tuning trains the model directly on specific data to alter its base behavior or communication style, acting like a closed book test. What are the key differences? 1. Data freshness and traceability. RAG is ideal for dynamic, frequently updated data because it pulls from a live database. It is also highly accurate and allows you to trace where the facts came from. 2. Behavior and formatting. Fine-tuning adjusts the model internal weights to teach its new skills, specialized terminology, or specific brand voice. Number 3. Implementation and cost. RAG requires setting up a retriever and a vector database infrastructures, whereas fine-tuning requires significant ML compute time and a high-quality dataset of prompt response pair. Number 4, hallucination. RAG limits hallucination by grounding answers strictly in retrieved text. Fine-tuned models may still hallucinate information outside of their core training. 3. What are the main components of RAG pipeline? You need three things: a retriever, a re-ranker, and a generator. The retriever finds the candidate documents, the re-ranker filters them, and the generator, usually an LLM, produces the final answer. Picture on the left, there are two main components. One, the injection, two, the generation. 1. Injection pipeline. This offline phase prepares your external raw data, saves it in a format optimized for rapid search. Data loaders, tools that extract raw text from various sources, databases, markdown files. Text splitters or chunking, breaking large document down into smaller readable semantic pieces or chunks so that the context window is not overloaded. Embedding model, an AI model that converts text chunk into highly high dimensional numerical vector capturing their semantic meaning. Vector store or the database, a specialized database like Pinecone, Milevus, or Chroma that stores the generated vector embedding alongside the original text for a quick mathematical lookup. The generation pipeline. This online phase triggers whenever a user asks a question to fetch contextual data and draft an answer. Query encoder converts the user's incoming text question into a vector using the same exact embedding model from the injection phase. Retrieval performs a semantic similarity search across the vector database to pull out the most relevant document chunks matching the query vector. Re-ranker, a secondary filtering layer that scores and reorders the retrieved chunk to ensure absolute high-quality context is prioritized first. Prompt augmented layer fuses original query with the pulled chunk into structured prompt blueprint. LLM, the generator. The core LLM that processes augmented prompt to output a contextually grounded and accurate response. Question number 4. What is hybrid retrieval? Hybrid retrieval mixes dense semantic search with sparse keyword search. Dense captures meaning, sparse ensures exact matches. Together, they balance recall and precision. How it works. A hybrid retrieval system merges the strength of two distinct search architecture. Sparse retrieval or keyword search. Use exact word matching (example BM25) to find precise terms, numbers, or specified product code. It is highly precise, but can't comprehend synonyms, intent, or misspellings. Dense retrieval, semantic or vector search, connects text into mathematical representation, that is, vector embeddings, to search by meaning. It understands that laptop and notebook are related but might miss exact identifiers like serial numbers. Now let's look at the workflow. When you perform a search, the system runs the query through both algorithms in parallel. It then synthesizes the result using merging technique to create a single cohesive ranking. Step 1. Retrieval. Both keyword and vector searches retrieve their own sets of relevant documents. Step 2. Fusion. The results are normalized and combined. Common technique used here is reciprocal rank fusion (RRF), which assigns scores based on where a document ranks in both lists. Step 3. Re-ranking. Many advanced systems passes the merged document through a third model that evaluate how perfectly the written text matches the user query. Hybrid search is important. Hybrid retrieval is a standard practice in RAG and modern AI applications. Number one, it gives better context. AI models receive precisely the right facts without being confused by irrelevant surface level keyword matches. It reduces hallucination. Loading LLM with exact data reduces generation of incorrect or fabricated information. Number three, flexibility. It provides it bridges the gap between literal meaning and conceptual understanding. Question number 5. How do we design a scalable RAG system? Designing a scalable RAG system requires decoupling your pipeline into independent indexing. This is done offline, querying, which is online layer, is done utilizing distributed frameworks like Ray to process millions of documents and employing hybrid retrieval strategies. You can use approximate nearest neighbor search, sharding, and caching. For real-time domains, you can add streaming injection pipeline. Scalability is about speed and freshness. For that, let's look at each piece of it and see how to achieve it. Number one, decouple data injection and indexing. To prevent your pipelines from bottlenecking when injection large data set, divide process into asynchronous microservices. Chunking. Break raw document into context-aware chunk with overlaps. Metadata attachment. Embed each chunk with tags like summaries, keywords, or department IDs to enable targeted pre-filtering. Distributed processing. Use asynchronous queues like Redis and Celery to parse embed files in background without blocking the application. 2. Scalable retrieval engine. Vector search alone often misses overlapping relationship. A scalable design combines multiple systems for high recall and fast retrieval. Hybrid search. Run traditional search in parallel with vector search. Re-ranking. Combine the results using reciprocal rank fusion and apply cross-encoder re-ranker for high-precision final results. Distributed vector database. Scale your vector stores horizontally using managed or distributed solutions like Quadrant or Pinecone to manage millions of documents without latency spike. Caching and request handling. As traffic increases, repeatedly passing heavy queries to LLM drains your resource and increases wait time. Semantic caching. Implement a cache layer to identify incoming queries that are semantically similar. Autoscaling. Use container orchestration like Kubernetes for your serving pipeline so that a compute instance can scale up during peak hours. Number 4, agentic routing and observability. Complex requests can overwhelm a single model. Using specialized agents handled by frameworks like LangGraph allows query to be broken down, researched, and verified in proper parallel. The last point to discuss is what is approximate near neighbor search. It is a technique that rapidly finds data points close to a query point in a large, high-dimensional dataset by sacrificing perfect precision for intelligent search paths. ANN reduces search time from minutes to milliseconds, making it the foundation for modern AI applications. Episode 2, Retrieval and Indexing. Question 6 to question 10. Question 6. How do you handle retrieval noise? You re-rank results with cross-encoders, apply confidence thresholds, and fine-tune embeddings for your domain. Noise reduction is critical for accuracy. Below is the strategic framework to filter out noise and improve generation accuracy. 1. Pre-retrieval optimization. You can achieve this by query rewriting or query decomposition. 2. Retrieval time controls. You can use hybrid search, metadata filtering, and document expansions. Number 3. Post-retrieval refinement. You can achieve this with similarity re-ranking or context comparison or context filtering. What is query rewriting? Use an LLM to rephrase and expand vague users' queries before feeding them to the search engine. What is query decomposition? Break down complex multi-part user question into smaller isolated subqueries to retrieve highly specific answers. Hybrid search metadata filtering we already saw in the previous questions. Document expansion. Generate potential questions for each document chunk during injection and index those questions to align with user search terms. Similarity re-ranking, which we already saw. Context comparison. Use an abstraction tool or an LLM to compress retrieved documents, strip out conversational filler, boilerplate text, or irrelevant tangents while preserving the core facts. Context filtering. Evaluate and classify retrieved chunk as correct or incorrect prior to generation, discarding anything that falls below a confidence threshold. Question 7. How do we optimize embeddings for domain knowledge? You fine-tune embedding models on domain corpora. For example, biomedical RAG uses PubMed embeddings. Specialized encoders make retrieval shorter. Okay, let's see different ways to achieve this. Number one, construct a high quality training dataset. The foundation of optimization is a dataset that contains query document pairs, typically formatted as query, positive document, and negative document. Number two, fine tune with constructive learning. Fine tuning adjusts the mathematical geometry of your vector space so that conceptually similar concepts are clustered together. Number three, implement hybrid search and re-ranking. We saw about this in previous questions. Number four, evaluate to prevent overfitting. Measure your embedding pipeline against the downstream metrics to ensure the model isn't losing its general capabilities. Question 8. How do we handle multi-hop queries in RAG? Handling multi-hop queries in RAG requires breaking down complex user questions into sequential logical sub-questions. The system iteratively searches the database for partial answers, then synthesize the finding and pass the reasoning trees to a large language model until a complete grounded answer is generated. Here are the core strategies with which you can achieve multi-hop queries. Query decomposition or chain of thought. You can use an LLM to automatically break a complex question into multiple simpler dependent subqueries. For example, if a query is where did the founder of the company that acquired Instagram go to college? System asks who founded Instagram first, followed by the second op query is extracting the name. 2. Iterative retrieval reasoning loops. The LLM evaluates the information gathered after the first hop. If critical context is missing, or if it requires connecting two distant pieces of evidence, then the LLM dynamically formulates a new query and pings the vector database again. Knowledge graph or graph RAG. Instead of relying solely on embedding, graph RAG structures data into explicit entities like people, organization, it's like Java classes, and relations to it, right? This typically allows retriever to traverse multi-hop connection before generating an answer. For example, company A acquired company B founded by person X. This is how you can handle multi-hop queries in RAG. Question number 9. How do we ensure freshness of retrieved data? We spoke about this in our previous questions. Anyway, I'll go through it quickly. You build incremental indexing pipeline, apply time to live policy, and stream updates. For finance or news domain, freshness is non-negotiable. How do we achieve it? In, Instead of relying on rigid scheduled patch builds, you can build your pipelines based on an event. When an event is triggered, then the pipeline updates the dataset. Configure expiration policy. In caching, set the expiration so that your cache will be refreshed time to time. I mean, you can use time to live or time to order for expiration policies. Monitor age and latency metrics. Actively measure how old is your data compared to what it is at the source. You can use time-based profiles or timestamping for this. Set up automated alerts. Catch pipeline failures, broken abstraction, or stale caches before end user do. You can do dynamic thresholding or monitoring to achieve this. Question 10. How do you chunk documents for retrieval? Again, we spoke about those in multiple times in previous questions. Uh, Chunk by semantic boundaries, not fixed lengths. Add overlap to preserve context. Never cut sentences midway. That breaks meaning. The most popular and effective starting approach is recursive character chunking. That is, using 200 to 400 token with the overlap of 10 to 20%. This method attempts to split text at natural boundaries like paragraph and sentences until the target size is met. Episode 3: Generation and Context. Question 11 through question 15. Question 11. How do you prevent hallucination in RAG? Preventing hallucination in RAG requires a multi-layered approach. Implement these core strategies across your pipeline to significantly reduce false output. Enforce strict prompt grounding. You need to program your system prompt to explicitly command the LLM to answer only using provided document, requiring it to output exactly I don't know if the relevant information is missing. Number two, improved retrieval quality. Hallucination usually stem from bad data. Combine dense vector search with sparse keyword search, that is that hybrid search we spoke about, and implement re-ranking to achieve this. Post inline citations. Require the LLM to cite specific source document or chunk ID in its response. This makes the model prove it works and prevents speculations. Add verification loop. LLM as a judge. Use a second post-processing verification step where another LLM assesses the generated response to check if it matches the retrieved context. If unsupported, block the output or trigger the regeneration. Apply contextual compression. Strip away irrelevant details from the long document before feeding them to the LLM. This stops the model from cherry picking bad data and avoid lost in the middle attention bias. Question number 12. How do you optimize context window usage? Optimizing a context window relies on prioritizing quality over quantity. Instead of dumping massive file into the prompt, strategically extract and compress information so the model only gets exactly what it needs for performing the task. How to achieve it? There are multiple approaches. Number one, retrieve and rank. Avoid parsing old knowledge base. Instead, use semantic chunking and re-ranking. Number two, context compression. Condense the information you do send into highly information dense format. You can use summarization, which we spoke about already, or prompt engineering. In prompt engineering, use clear instruction and specific few short example rather than a verbose or unstructured data. State management and compaction. For ongoing workflows or long chat sessions, actively manage accumulating context to prevent performance degradation, or known as lost in the middle. You can use slide window, that is discard the early parts of the conversation or previous tool outputs, or you can use context compaction. Periodically summarize long histories to preserve critical details and reset the context window to free the tokens. Number 4. Isolate workflows. Uh, to avoid overloading a single agent with massive context window, you can break the task into multiple tasks and hand it over to multiple agents to avoid this scenario. Question 13. How do you handle conflicting retrieved document? When retrieved documents present conflicting information, RAG system is explicitly instructed to avoid arbitrary guessing. Instead, it uses multi-step resolution process to ensure transparency and accuracy. You could use one of the structured frameworks below to achieve this. Explicit acknowledgement. The model is guided to flag the disagreement directly, making the user aware that there is multiple options. Metadata and source ranking. Wherever possible, model analyzes document meta to prioritize the most recent or reliable data. Contextual breakdown. Instead of summarizing contradiction into an average, the model is instructed to lay out the different viewpoints and explain the context or rationale behind each. User consultation. When source credibility or user intent is unclear, model present the findings and the differences to the user on which data to prioritize. Question 14. How do you integrate structured data into RAG? To integrate structured data into RAG, use a hybrid approach matching the data source format. For relational database, deploy text-to-SQL agents to generate and execute queries dynamically. For files like spreadsheet or tables, use data-to-text convert rows into natural language before embedding. Or store categorical values as metadata for filtered retrieval. You can use multi-source orchestration to route the user query to appropriate tool, decide whether to search a vector database or run a query or make an API call. Question 15. How do you combine RAG with agentic AI? Agents use RAG as a tool, retrieving context before reasoning. They can orchestrate multi-retrieval steps, validate answer, and escalate when retrieval fails. This makes RAG part of large autonomous workflow. Episode 4. Reliability and Evaluation. Question 16 to question 20. Question 60. How do you evaluate a RAG system? Evaluating a RAG system involves accessing its retrieval component and generation component separately. Key metrics include context relevance and context recall. Context recall is for retrieval side. Alongside faithfulness. Faithfulness means no hallucination. Answer relevancy and answer correctness for the generation. What is context relevance? Does your retrieval fetch information directly addressing the user query? Is context relevance. Faithfulness is no hallucination. Is the answer generated grounded on the retrieved context or the content? Is faithfulness. Answer relevance. Does the final response actually address the user initial question? Is answer relevance. Move on to question 17. How do you measure hallucination rate? Compare the generated answer against ground truth or retrieved context. Track unsupported claims. The lower the hallucination rate, the stronger the system is. You can measure hallucination with the below approaches. Automated drag and LLM as judge. Use framework like Deep Evolve or Brain Trust to grade responses in real time. You can measure faithfulness metrics and groundness metrics using these approaches. Number two, fact extraction and benchmark. This is done offline. For standard question and answer, break down the output into atomic facts and check them against the curated ground truth datasets. 3. Semantic similarity. Calculate the similarity between model's answer and ground truth context using vector embeddings. Number 4. Human evaluation and user feedback. The gold standard is still human in loop review. This is tracked by having subject matter experts, samples and labels generation as hallucination or factually correct. These four ways with which you can measure hallucination rate. 18. How do you test retrieval quality? To test retrieval quality, build a ground truth dataset of queries with expected documentation. Run searches against the set and calculate quantitative metrics like recall at k, that is, did you find the necessary info, and precision at k, how much junk was written. And finally, use LLM as judges for semantic relevance. Okay, let's look at how to do ground truth dataset. You can use manual labeling. You can ask an expert to read through the queries and manually identify the exact source text record, or you can use synthetic generation where you use a powerful model to read your knowledge base, generate realistic questions, and trace them back to the source chunk. How to measure core retrieval metrics. We already looked at recall at key and precision at key. The third one is mean reciprocal rank. This evaluates the ranking quality, or you can use normalized discount cumulative gain, that is NDCG at K. This is a graded metric that accounts for both relevance and ranking position. It heavily penalizes the system if a rank 1 is branded as rank 5. How do you monitor RAG in production? To monitor RAG pipeline in production, track three main pillars: performance, that is latency plus cost, retrieval quality, and generation quality. Use specialized observability tools to continuously evaluate these components rather than just relying on standard API logging. Create dashboards to track latency, cost, retrieval hit rate, and user feedback. Continuously monitor to ensure you catch drift and failures early. Number 20. How do you handle partial retrieval failures? Partial retrieval failures are handled through graceful degradation and automated fallback mechanism. When some, but not all, data sources or database shards respond, the system isolates the unavailable component and synthesizes an answer using only the successful retrievers, while clearly notifying the user of incomplete context. What it means: fall back to cache results, retry subsets, or degrade gracefully with no answer as response if you don't find anything. The motto is never let the system crash silently. Episode 5: Governance and Future. Question 21 to 25. Question 21: How do you enforce compliance in RAG? Enforcing compliance in RAG requires a multi-layered approach that integrates data governance, access control, and output guardrail into every stage of the pipeline. Failing to properly secure the systems often leads to data leaks and severe regulatory penalties. There are four core pillars to get achieve this. Number one, injection and indexing. This serves for data governance. Metadata tagging. You attach structured attributes like sensitivity level, regulatory frameworks, or regional tags directly to vector embeddings during injection. Data masking and data de-identification. Implement named entity recognition, that is NER, to automatically detect mask or replace all PII and PHI data. Number two, retrieval time authorization, fine-grained access control. Don't rely solely on database rules. Ensure identity-based or relationship-based filters at the query level so the system only searches document it is authenticated to. Least privilege retrieval. Configure the retriever to only fetch the minimal necessary context for LLM to process. Number three, generation and output guardrails. Deterministic filtering. Use deterministic guardrails, role-based filters, and allow list alongside probabilistic LLMs to block sensitive or outbound topics. Source attribution and traceability. Require the LLM to cite specific sources, regulation IDs, and versions. Use tools like RAG evaluation, like RAGAS or TrueLens to measure faithfulness and ensure generated response relies solely on the retrieved document. Number four, audit and monitoring. Immutable logs. Log the complete RAG transaction as a immutable audit trail. This includes the query text, the user ID, retrieved chunk hashes, the prompt, the LLM output, faithfulness score, and the timestamps. Continuous evaluation. Routinely scan your RAG system for data leakage, model drift, and hallucination pattern to maintain defensibility against evolving regulations. 22. How do you secure RAG pipeline? Securing a RAG pipeline requires implementing a zero trust approach across all four stages: data injection, retrieval aware access control, model execution, and output validation. This prevents sensitive data leaks and stops prompt injection and guarantees data privacy. There are four parts to it. Number one, data injection and sanitization. Number two, retrieval time authorization. Number three, model and retrieval defense. Number four, output validation and monitoring. Number one, data injection and sanitization and retrieval time authorization we already covered in our previous question. Number three, model and retrieval defense. How to achieve it? Instruct Instruction hierarchies instruct the LLM to prioritize the system prompt over retrieved context and retrieved context over raw user query. This hardens the system against malicious instruction hidden inside an indexed document. Vector store hardening restrict API access to your vector database. Enforce encryption at rest and in transit and use mutual TLS for communication between embedding service and the database. 4. Output validation and monitoring. You can use output filtering by using guardrail frameworks like NVIDIA NeMo guardrails to scan generated responses for PIA or PHI leaks or hallucinations. Audit logging, maintaining a logging of semantic intent of the query, vector ID used for context, and responses for the forensic analysis and compliance. Question 23. How do you handle multilingual retrieval? Multilingual retrieval is handled using specialized strategies, primarily depending on the system architecture. The most modern pipeline involves multilingual embedding models. In this, documents are chunked and converted into vector representations using language agnostic embedding models like BGEN3 or Cohere. Incoming queries are mapped into the same vector space, enabling semantic matching without needing direct translation. Second, the hybrid search. Standard keyword search like BM25 or combined with dense vector searches to improve cross-lingual precision. Third, query or document translation. Sometimes the query is translated into English or the document language via machine translation. Use multilingual embodies like Labase or Muse. Normalize queries across languages. This makes RAG global ready. Question number 24. What are the biggest challenges in enterprise RAG adoption? Enterprise RAG adoption often stalls because of structured data hurdles and security mandates. The biggest roadblocks include data fragmentation, poor retrieval accuracy at scale, maintaining strict access controls, and preventing sensitive data leakage. Enterprises want reliability, not just novelty. Now let's look at each of this. 1. Data fragmentation and silos. Enterprises houses vast unstructured knowledge across disconnected platforms like SharePoint, Salesforce, Slack, and legacy database. Dumping this data into a flat vector store destroys vital temporal and contextual relationships, resulting in fragmented information. Number two, retrieval accuracy and chunking. Native RAG pipelines suffer a steep drop in precision when scaling up. Complex formatting such as multi-column PDFs, tables, and charts can result in parsing error and loss of context during data injection. Permission-aware retrieval. Maintaining corporate governance and role-based access control is paramount. A major stumbling block is building RAG pipelines that restricts LLM from surfacing information to an unauthorized employee. Question 25. What is the future of RAG? RAG is evolving from simple vector search into highly iterative, modular, reason-driven architecture. This shift, often called agentic RAG, combines with intelligent search with function calling, knowledge graph, and multimodal retrieval, allowing system to dynamically fetch and process data in multi-step listening loops rather than one-shot queries. The future is multimodal RAG, text, images, and structured data together. This will integrate with agentic AI, real-time retrieval, and governance framework. RAG will become the backbone of enterprise AI. Thank you. And that's the complete set of 25 advanced RAG interview questions and answers. With this, you'll be ready to impress in 2026 AI's ML interviews. Don't forget to like, subscribe, and share for more AI prep content. Good luck on your journey into advanced RAG systems. Bye bye. It's Pradap Gopal signing off.